In the last lecture, we have already discussed about how to do community analysis, and we have seen quite a few techniques to do community analysis. So, and we also started with this concept of spectral bisection. So, today we will continue with this idea of spectral bisection. And in order to do spectral bisection, last class I already defined two basic matrices that we will need for the rest of the analysis. One is what we call the incidence matrix, and the other is the Laplacian matrix. So, the incidence matrix, as we said, is a n cross E matrix, where if there is a edge E I j, then for the column E and the entry point I, we have -1, while for the entry point j we have +1. So, we will look at a typical example soon. We also looked into the definition of the Laplacian matrix, which is the diagonal entries are the degrees, whereas the non-diagonal entries for each cell where there is an edge we have the corresponding entry equal to -1. So, that is how we define the two basic matrices, the incidence matrix as well as the Laplacian matrix. So, now we will take an example and see how these two matrices are constructed given a undirected graph. So, let us take a very simple example and start. Let us say we have this graph. This is basically a line graph of 5 nodes, 1, 2, 3, 4 and 5. Now, the edges can also be numbered. This is edge 1, edge 2, edge 3 and edge 4. So, now as we have defined, the incidence matrix would look like this. So, as we have said, it is a n cross E matrix. So, basically it will be like this. We have the n's here 1, 2, 3, 4 and 5, whereas we have the e's on the columns 1, 2, 3 and 4. Now, we see that between the node 1 and 2 we have an edge. Okay. So, one entry point becomes -1, while the other entry point becomes +1. Similarly, we see that we have an edge between 2 and 3. So, in the column of 2, which is the column of the edge 2, okay, we have one entry point as -1 at 2 and the other entry point as +1 at 3. In this way, we have an edge between 3 and 4. So, in the column of 3, we have one entry point as -1 here and one entry point as +1 here, and similarly for the last case we have one entry point as -1 here and one entry point as +1 here. So, in this way we can construct the incidence matrix. Note that each column here represents a particular edge, edge number 1, edge number 2, edge number 3, edge number 4, and if the edge is between points I and j, then point I gets -1, point j gets +1. In this way we have constructed the incidence matrix. Similarly, we can also construct the Laplacian matrix. So, as we said that the Laplacian matrix is a n cross n matrix. So, you have 1, 2, 3, 4, 5 n 1, 2, 3, 4, 5. And now each entry. So, as you see the diagonal entry is nothing but the degree of the node. So, here the diagonal entry for 1 1 is the degree of the node 1 is 1. The degree of node 2 is 1 plus 1 2. The degree of node 3 is 1 plus 1 again 2. The degree of node 4 is 1 plus 1 2, and the degree of node 5 is 1. So, in this way you can construct the degree of each of the nodes, and in this way the diagonal entries are filled up. Now, look at the other entries. So, there is only one edge between 1 and 2. So, 1 and 2 there is an edge. So, you put a -1 here. There is no other edge. So, in the at least in this particular row. So, the other rows become, the other entries are equal to 0. For 2 1, so 2 1 you have an edge. So, this is -1, and you also have a edge from 2 to 3. So, this is -1, rest is 0. Similarly, for 3 1 you do not have any edge. So, it is 0. From 2 3 2 there is a edge, and from 3 4 there is an edge. So, you have -1 entries here and you have 0. So, 1 4 you do not have any edge, 2 4 you do not have any edge, 3 4 you have an edge. So, it is -1, and 4 5 you have an edge. So, it is -1. So, for 5 all the entries are 0 except 4 5, which is a -1, okay, at the entry 5 4. So, now you see the interesting property of this particular Laplacian matrix is that sum of each individual row is always equal to 0. You see this row, take this row, the sum is 1 plus -1 plus 0 plus 0 plus 0, that is 0. Okay. So, it is -1 plus 2 -1 plus 0 plus 0, that is 0. So, in this way sum of all the rows is equal to 0 in this particular Laplacian matrix, and this Laplacian matrix can also be written as D minus A, where D is the diagonal matrix, containing degree of nodes, and A is nothing but the adjacency matrix. So, basically if you implement D minus A, you will recover the Laplacian matrix. Okay. So, now with these two notions of the incidence matrix and the Laplacian matrix, we will introduce certain properties which will finally allow us to actually do a partitioning of the graph based on spectral ideas. Okay. So, some of the properties that these particular matrices follow are that I write here. Number 1 is that LG, which is the Laplacian matrix, is symmetric. Therefore, its eigenvalues are real and orthogonal. Sorry, the eigenvalues are real and the eigenvectors are real and orthogonal to each other. So, basically since it is a symmetric matrix, since LG is a symmetric matrix, because the graph G is an undirected graph, so that is what is our assumption to start off with. So, since we assume that graph G is an undirected graph, so we have a LG matrix, which is a symmetric matrix in this case, and therefore all the eigenvalues are real and the eigenvectors are real and orthogonal, that is perpendicular to each other. The vectors are perpendicular to each other in the vector space. Okay. So, that is the first property. The second property is that if we have a vector say E which looks like this 1 1 1. So, this is a vector of all ones. Okay. The column vector of all ones. Okay. So, then we have LG into E is equal to 0. So, why this is true? So, for instance, if you look at the previous example that we have seen, so take this example. So, here as we have seen that sum of all the individual rows is equal to 0. Now, if you put a column vector of all ones, what will happen? The first entry will not do nothing but sum all the entries of this particular row. The first value, the product with this one, will not do nothing but sum all the entries of the first particular row. Similarly, the multiplication with this one will sum all the entries of this particular row. So, the sum of this first entry is equal to 0, as you know, the second entry is equal to 0, and so on and so forth. Therefore, we have from this observation we have this particular interesting property that LG into a vector of all ones is equal to 0. Now, we have two more important properties which we will prove in a while. Let us first write the properties. The incidence matrix multiplied by the transpose of the incidence matrix, this actually returns the Laplacian matrix. So, the product of the incidence matrix and its transpose together, actually this product, the incidence matrix and the transpose of the incidence matrix, that actually returns you back the Laplacian matrix. So, this is a very nice property which we will be using in a while. And the fourth property is that the Laplacian multiplied by an eigenvector v is equal to some constant lambda into the eigenvector v. So, where lambda is the eigenvalue. So, this actually tells you that lambda is equal to nothing but sum of all edges, sum over all edges V I minus V j whole square by sum over all nodes V I whole square. So, basically what this says is that lambda. So, if you look at this formula, the expression at the numerator is a sum of the squares, whereas expression at the denominator is also a sum of the squares. So, both of them have to be positive and therefore, the ratio has to be positive. So, the lambda values are positive. That is what we will prove in a while. Then there is this fifth property which says that the eigenvalues of LG are, as I said, non-negative and ordered as 0 less than equal to lambda 1 less than equal to lambda 2 less than equal to lambda 3 and up until less than equal to lambda n. So, in this way you can order the different eigenvalues of the Laplacian matrix. Okay. So, and then you have the last property which tells you that the number of connected components of G is equal to the number of eigenvalues equal to 0. Okay. In particular, if the eigenvalue lambda 2 is non-zero, then the graph is connected. So, basically this is why, as I was telling you last day, the second eigenvalue is very important. So, if so there is one point to consider here, since we are assuming the Laplacian matrix which is D minus the adjacency matrix, we are interested in the second smallest eigenvalue. If on the other hand we deal with the adjacency matrix directly and look at its eigenvectors and eigenvalues, then we will have to look into the second largest eigenvalue. Since you are looking at a matrix which is D minus A, so you have to look into the second smallest eigenvalue. Okay, and here the second smallest eigenvalue, as we have noted, is lambda 2, and if lambda 2, especially if you observe that lambda 2 is not equal to 0, that means there are more than one connected component in the graph. Okay, that means the graph is disconnected. So, if this is non-zero, then only you have the observation, then only you can make the observation that the graph is connected. Okay. So, now one by one we will prove properties 3, 4, 5 and 6. So, proof of property 3. So, this is a very easy proof to see. So, now assume the product of ing and ing transpose. So, this actually, if you are considering the cell JJ, that is the cell where it is a diagonal. Okay. So, imagine the matrix. So, you are considering the diagonal values. Now, the diagonal values in this particular matrix, in this particular product, will be nothing but actually -1 square or +1 square. Okay. So, depending on whether j was assigned a -1 or a +1. Okay. So, it is either -1 square or +1 square, and this will sum over all edges that point to the node j. So, basically this will sum over all edges that point to node j. So, what are the all edges that point to node j? If you have this node j, and so each will have come with -1 or +1, -1 or +1. Now, you are taking a square of this. So, basically that gives you nothing but the degree of the node j. So, basically you have shown half of it. So, you have shown that the diagonal entries of this product matrix, okay, will be equal to the degree. Okay. So, as we have seen in the Laplacian matrix also, the diagonal entries are nothing but the degree of the nodes. So, that part we have already shown. Now, we are left to show the thing for the other part. So, now again consider ing times ing transpose, but now I and j are such that there is an edge between I and j. If there is an edge between I and j, then what you will have? Either you will have -1 into +1 or +1 into -1. Okay. This is because one side is I and the other side is j, and there is a edge connected between them. If this is -1, then this is +1. If this is +1, then this is -1, as per the definition of the incidence matrix. Now, if you take a product, it will be either -1 into +1 or +1 into -1. So, this leads to -1 if there is an edge existing between Aij, and that is what is exactly the definition of a Laplacian matrix. Okay. So, we have shown that the product of the incidence matrix and its transpose will give you in the diagonal entries the degree values, and in the non-diagonal entries if there is an edge between the two nodes corresponding to that cell, then it will be a -1. So, that means this is exactly equal to the definition of the Laplacian matrix. So, that is why we have proved the property 3, which says that Lg is equal to Ing into Ing transpose. So, we have this is how we can easily prove that there is a relationship, there is an interesting relationship between the incidence matrix and the Laplacian matrix. Next, we will have to look into the proof of property 4. Now, what have we seen in the property 4? That Lg multiplied by an eigenvector is nothing but lambda multiplied by an eigenvector. So, now we can write something like this: V transpose Lg star V is nothing but V transpose star lambda star V, where V transpose is the transpose of the eigenvector V. So, now since V transpose is the transpose of the eigenvector V, so if you take a product of V transpose V, this will be nothing but a scalar value. So, that means we can write V transpose star Lg star V is equal to lambda, we can take as out as constant, V transpose star V. Therefore, we can write an expression for lambda as follows: this is V transpose star Lg star V divided by V transpose star V, and we can do this division since V transpose V is nothing but a scalar, because you are multiplying the eigenvector with its transpose. So, it will translate into a scalar value, it is no longer a vector. So, now this can be further simplified. So, V transpose into, so now Lg, you know that Lg is equal to Ing into Ing transpose. So, you can put this in the formula and rewrite the expression as Ing multiplied by Ing transpose times V by V transpose times V. Now, we will call y is equal to Ing transpose V. That will imply y transpose is equal to V transpose Ing. So, using this, replacing this expression by y, you have V transpose into Ing is nothing but y transpose into y divided by V transpose into V. So, we have nicely simplified the expression to y transpose multiplied by y by divided by V transpose multiplied by V. So, now what is V transpose multiplied by V? So, now we can further rewrite lambda as, so the denominator V transpose multiplied by V is nothing but square of Vi's, sum over all i's basically. So, the V transpose V is nothing but you are taking each entry of V multiplying with it with V transpose as entry, that will give you Vi square for each entry point I, okay, for each node I, whereas the numerator is nothing but sum over all edges y e whole square, because you are now looking at the incidence matrix. So, the incidence matrix is defined on the edges. So, one side of the edge is I and the other side of the edge is j. Two nodes are there, the node I and the node j, and now if you multiply ing transpose into V transpose into ing, this will give you nothing but the square of these values. Okay. So, basically if there is an edge Eij, for the edge Eij, we can easily see that Ye is nothing but, so Ye is nothing but, so you have one entry for Vi and the other entry for Vj, right. So, you have one entry for the node I and the other entry for node Vj. So, what you are doing, you are basically multiplying the V vector with the incidence matrix. So, the V vector is nothing but V1, V2, V3 up to Vn, all the individual entries for each individual node, and the incidence matrix is nothing but a +1 for one end of the node and a -1 for the other end of the node. So, you have Vi into a +1, then Vj, the other end of the node, will have a -1. Okay. So, you will either have Vi minus Vj or Vj minus Vi. So, it is either Vi minus Vj or the opposite, Vj minus Vi. This comes from the fact that you are multiplying the vector of entries in V with the incidence matrix. So, the vector of entries, if at one point the vector is Vi and at the other point there is a vector Vj and there is an edge between these two vectors, then you will have, for Vi you will multiply with +1, whereas for Vj you will multiply with -1, since there is an edge between them, and then you will have, when you sum, you will have Vi minus Vj. Okay. So, these you will get this for each individual edge. So, therefore, you can write lambda is equal to Vi minus Vj whole square sum over E divided by sum over I Vi whole square. So, in this way you have come to the conclusion that the numerator as well as the denominator of this expression is a sum of squares. So, therefore, each of them is positive and therefore, this whole expression is positive. So, in the next lecture we will continue proving the next two properties.